All right, okay, good afternoon. Let's get started. We're almost done with network layer. Last time, we discussed routing algorithms, right? Dijkstra, which is link state, and distance vector. Okay, and then we pointed out last time that so far we've been thinking about one source, one destination, which is the so-called unicast problem. All right, great. And so I want to wrap up network layer by talking about slightly different network architecture or topology in which you have multiple sources and multiple destinations. Okay, we'll call that broadcast and multicast. So in some sense, broadcast and multicast are almost the same problem. All right, so the idea is you have multiple, so in one instance of the problem, you have multiple destinations. Okay, so let's still stick with single source, but multiple destinations. So for example, in a scenario where you have a radio station or television station that's broadcasting, and you have many people receiving, right? You could have a football match being broadcast on the internet, or you have these internet radio stations, and multiple people want to listen. Right? So imagine that scenario, single source, multiple destinations. So in this example network here, R1 is the source, and suppose that R3 and R4 are the two destinations, and R2 just happens to be a relay. Okay? For example, for the purposes of this example, it doesn't matter whether R2 wants the data or not. So the solution that we would use if we went with the unicast idea is we'd create multiple unicast routes from R1 to R3 through R2, let's say, and from R1 to R4 through R2. I think in this example, I also said R2 is a destination. So there's a unicast route from R1 to R2. So you see there's, on the left, three unicast routes. But you see a little problem, right? R2 is getting the packet 3 times. Yeah, so we want to try to address that. Given that we know R2, R3, R4 are all wanting the packet, can we do better? And so we could, for example, send it to R2 once, and somehow if we could instruct R2 to duplicate it, to forward it on both its interfaces. Right? R2 has 2 interfaces, R3 is available on one interface, R4 is on another interface. Right? Then you can see that by doing in-network duplication, you can perhaps reduce the total number of transmissions. Now, there are many ways that you could define, for example, the inefficiency of the left-hand side. And we're not going to get into that. Right? You could talk about number of transmissions, number of duplicates, and all that stuff. But let's not worry about that. But you get the idea. On the left, you see there's a left I'm going to call source duplication, on the right in-network duplication. And so this is sort of motivating the idea of having something happen inside the network, some duplication happening inside the network. Okay? Now if you look at this example on the right, you might think, well, okay, I could just put nodes, or I could specify packets to have a certain flag that indicates this is a broadcast packet, right? And then nodes could treat it differently. So what could they do? So let's say we now know that a certain packet is a broadcast packet, and for this example, just assume everybody in the network wants it, just like DHCP, right? When a DHCP, when a new client comes to a subnet and wants to get an IP address, in some sense it has to broadcast to everybody in the network because it doesn't know the DHCP server. So imagine it's that type of situation where every node wants the packet, so you identify the packet with a certain flag, right? It's part of your protocol. So what could nodes do? Well, there are many things that nodes could do. The simplest is, whenever I receive a packet, I forward on all of my interfaces. That's flooding. Okay? And so that will work, right? Then the packet will get to everybody because this is a connected network. It's probably not that great because when R2 gets a packet, it will send to R3 and R4. But if R3 also has the sort of protocol that it's going to if it, once it receives a packet, it's going to send it out. It's going to send it to R4, and R4 will send to R3. So in some sense, there's also some inefficiency there. So you could do controlled flooding. You only forward a packet if you haven't seen it before. So maybe in that case, they won't keep flooding the packet. So you're only going to broadcast a packet if you have not seen it. That still will result in some mild duplication, some mild inefficiency. I mean, there's no way actually to remove all inefficient or duplicate transmissions, not in the current way we have it set up. In fact, that's what we're going to try to head towards, right? And you can probably guess how we're going to get there. Okay? Can anybody guess how we're going to get there? What's the reason in this example here for having some, even if you do controlled flooding, some mild, so what the controlled flooding does is it stops the flooding. But there's still some duplicate transmissions, right? Because R3 will send to R4, but R4 already has it from R2. But R3 doesn't know that. So what's the problem here? Or how might you fix it? Just curious if you can guess. Not really, because there's no reason for R3 and R4 to communicate yet. Well, I mean, you'd want to maybe broadcast or flood only on a subgraph, right? And that subgraph would be some sort of tree, like without a loop. Yeah, so that's what we'll head towards. We'll head towards constructing a tree, and specifically, what type of tree? A spanning tree, right? Because it has to reach all the nodes. And the only difference between like broadcast and multicast is, well, in multicast, not all nodes are part of the set of nodes that want the packet. So you'd want to build a spanning tree that contains your nodes, the routers that contain the nodes that want the data. Okay, so I mean, I think it's important to understand problems, right? Because there are an unbounded number of solutions. So it's better you understand the problem, so that if you get into a new situation, like you're working for new ISP, and you come across this problem, yeah, you have to solve it, but in the context of that ISP. Right? So it's better you understand problems, because problems don't go away. Solutions will have to change based on context. Okay, so we basically figured out what the problem was, what the inefficiency was, how you might solve it. Those solutions have some inefficiencies. Eventually, we want to build a spanning tree. Okay, so now we've already seen spanning tree before. Where do we see it? Where has spanning tree come up? Like we looked at an algorithm that generates a spanning tree. Yeah, Dijkstra generates a spanning tree, and it generates, well, an efficient spanning tree, a shortest path spanning tree. So let's see if we can use that. So look at the left. Let's say A is the sender, and all the other nodes are potential receivers, destinations. Well, the solution is simple, right? You just need a spanning tree rooted at A. So exactly Dijkstra works here. The shortest path rooted at A. Okay, so for example, I think the dark edges here are the spanning tree rooted at A, right? The light edges are other links in the network, but they're not part of the spanning tree. So this is when the broadcast is initiated at A. So of course, if you now do this, and you do flooding on this, you're golden, right? Everything's good. There's going to be no loops or so-called broadcast storm cycles, okay? Now, the main problem with the solution on the left is, suppose that D also now wants to send to all the nodes in the network. And if D uses this spanning tree, we have a problem, right? I mean, it'll still work, but it's a bit inefficient because D has a direct connection to E. But on that spanning tree, it has to go DBACE. So it's a bit inefficient for D. So this raises the question, if you have multiple sources and multiple destinations. For example, so the situation on the left models where A is like a broadcaster broadcasting the World Cup, and B, C, D, E, F, G are customers. It's perfect. But the situation where you might have any node be a sender models like an online game. Let's say we're all playing an online game, and we're all in the world, like we're in Minecraft, right? Or some Roblox game or whatever, I don't know. What do people play now? I'm going by what games my son plays. Do you guys game? Is anybody here a gamer? Like, give me one game that I can learn from you. You guys are learning from me, and I should learn something from you. Like, what's a game that's very popular right now? League of Legends. Isn't that an old game? It's still popular? I have no idea. One I've never played it. I just remember from it from many years ago, right? It's not new, right?
No, it's not.
Okay, yeah. But okay, so League of Legends. I also remember things like Fortnite. Is that, people still play that? Right? No one plays that. What? What? Okay. What do you adults like? What? Like League of Legends? What do you play? Okay. I also remember like Grand Theft Auto. Like, does no one play that? That's like my time.
They're releasing new ones too.
Oh, are they? Okay. Yeah, I remember I used to. I'm not a gamer, but these are Roblox, which is a platform, which there's lots of games. That's all my son plays. That and sometimes Minecraft. Yeah, but in those games where there's a world and you have multiple players, when you make a move in the world, everyone needs to know that, right? It needs to reflect that. So in some sense, every node is a sender, every node is a destination. And in that case, it begs the question, okay, you still want a tree, but you don't maybe want a tree rooted at one node. So you ask the question, is there a shared tree? Right? So you could potentially just count the number of trees, right? I mean, it's a combinatorial problem. It's not easy. It's a combinatorial problem, and there's no fast solution. You have to just search. You can search for all trees, and then based on, I didn't put edge costs here, but you need some labels on the edges, edge cost. You could say, given a tree, the cost of a tree is the sum of all the edges in the tree. And then you could say, I'm going to find the smallest, yeah, so you have to be careful. It's like so in Dijkstra we talk about least cost spanning tree, but that was rooted at a node. Here it's a shared tree. So sometimes they call it a minimum spanning tree, right? And there's also this idea of Steiner tree. Okay, and so I think if you can understand that, you pretty much understand very broadly, without algorithms, what the issues are in broadcast and multicast. Okay, so this sort of raises the idea of a shared tree. And then I think this is just saying that, well, multicast is just a subset of broadcast. Right? In this example here, like these nodes here, this router, they're not part of your, they don't have any customers hanging off it, of the broadcast. You know, assuming the broadcast starts at, let's say, this node here. Okay, but the other routers do. So multicast is just a subset. Okay? And then yeah, we can just find a shortest path tree. And we studied only one example, which was Dijkstra, right? But it turns out there are many examples of algorithms for finding shortest path in a graph. Okay, so this is actually my last slide. So we motivated the idea of a shared tree, okay? And there's two notions there. There's minimum spanning tree, which is like amongst all possible trees, which one has minimum cost. Then there's the notion of Steiner tree. Steiner tree is, so both minimum spanning tree and Steiner tree involve a shared tree. The question is, what nodes are you allowed to transmit through? Okay, meaning, like if there are certain nodes in your graph that are not destinations, can you still use them to do better? If you want to do that, you get the Steiner tree, and that becomes an NP-hard problem. If it's just amongst, let's say, a certain set of nodes, and that's all you're allowed to use, you can actually find more efficient algorithms, and that's the minimum spanning tree. Okay, because it's a tiny bit confusing, I actually have If you look in Canvas, I prepared a handout for you which discusses Steiner trees and minimum spanning trees. Yeah. Okay, so you can read this, yeah. So this just explains the difference between the minimum spanning tree and the Steiner tree. Okay, but it's roughly the same problem of finding a good shared tree. Okay, so I think with that we'll come to the sort of end of network layer, right? Are there any questions? No? So I knew we were going to end a bit early, so what I did was, actually I have a little assignment for you. Yeah. Okay, you go to activity 29th March. Actually, it's due in class. I'm going to change it to end by the end of class. Okay, so it's a class activity. It's not homework for you. I already have given you homework. You're working on the homework, so I don't want you to think I'm giving you more homework. This is for class, and then we'll discuss it. Okay, and then if there's time, we can discuss the Steiner tree and shared tree more as well. Okay, so please go to this. There's a handout here. If you open this, there's a password. I'll give you the password. It's Singa 2024, all lowercase. SINGA 2024. Okay, and again, it's due in class, so please work on it now. Yeah, we have plenty of time. In case you didn't catch that, that's the password. Sorry, all lowercase. Let me actually download it. I don't have it. Okay, this is about network layer. Okay, it's kind of what we talked about last time. There was 4 questions. Okay, and I promise you we will do an aggregation problem. So that's the aggregation problem. And you can enter it just in line. If you go to Canvas, like if I go to student view and I start the assignment, you should see like this box here. Just enter, like 1, whatever, 2. Okay. Let me see if I can find you a good example of shared tree and Steiner tree. I have one, but I will find you a good example. Okay, how's it going? Let's okay, so are we have we submitted this yet? What were the 4 problems? So please submit by class today. So I'm going to just set it up so that. Give me a second. Oh, I'm still in student view. Okay, how about? Wait. So our class is what, 1 to 2, right? 1 to 2. Okay, hang on. So 1401. So today. Okay, and I think I have a copy of it. Let me open it up so we can discuss it. Okay, can we, question 1, what does that mean? This guy's simple, right? What does /24 mean? Subnet mask, but what does it mean? Yes, I agree, it's called the subnet mask, but what does it mean? Okay, that's the subnet, correct, the subnet mask, but what does /24 mean? Yeah, there's 24 bits. Of the 32-bit IP address, 24 bits are the subnet identifier. Okay, that's what kind of. So in this case, you can figure it out. It'd be 212.56.132 is the subnet identifier. Okay, so then the second question is related. I don't know why I changed it, but we could do the first one too. So if a subnet ID is 199.34.32/27, how many addresses are in this subnet? How would you figure that out? Okay, so remember, there's a subnet part, and then that's fixed for the subnet. That means all the nodes in that subnet have the same subnet part. What they have different is the remaining bits called the host part. So if I have 27 bits in the subnet part, how many bits in the host part? 5. So how many addresses are in the subnet? Yeah, so do you see it's not 2 to the 27, Zichin, right? It's 2 to the 5. Now, you did 2 to the 5 minus 2. Why did you do that? Yeah, she said it. Hang on, just yes. You're on the right track, but I want to ask her.
Because all zeros and all ones are taken for other purposes.
But what did I ask you? How many addresses are there? There's still 2 to the 5. So anyway, just be a bit careful, right? You're correct in the sense that if you ask how many hosts can be supported in this network, yeah, it's 2 to the 5 minus 2. Okay? Yeah, correct, yes. So I think you guys got that right. How about the third one? How are you going to aggregate these 4 subnets into, so if there was ISP that was handling these 4 subnets, what prefix would this ISP need to advertise? How would you find it? Yeah, you'd turn this into binary and look for the place that they match, right? The longest set of matches. So in this case, did anybody do it?
It's 110. The first 2 bytes of the same, then 100001.
And what's the?
It's like ish. Like.
Yeah, but okay. So how do you aggregate it? What's your final answer?
110101001001000100001.
Okay, so something like, so this was, we know that this was what, hang on, draw. Right? This was 24 bits in the subnet part. This is 2 to the 5 addresses. Okay, hang on. Yeah, I'll come to you in a second. Give me a second. Let me just, I realized I wasn't writing it. To the address or 2 to the 5 minus 2 hosts. For this one, you're saying it's 212.56.132 slash what? 22. Yeah, I think that's the important part. The slash 22 changes. That's why this is a different subnet than the slash 24. Okay, but yeah, you just expand these out and look for, so in this case, you just got to convert 132, 133, 134, and 135 into binary and figure out where they match and where they're different. Okay? All right, how about this one? So the idea here is to find Okay, and how about this? Hey, by the way, you see that, so this is going the other way, right? This is called aggregation. We could have done splitting, right? If I give you a subnet and I say split it into multiple, right? It's a two-way process, right? Both are very similar. Okay, how about question 4? Yeah, so here x is an integer, so my network looks like this, and we need to figure out when Dijkstra works, okay? So what we mean, so remember, just some facts about Dijkstra. Dijkstra will always terminate, and Dijkstra may or may not find the correct answer, meaning it may not find the true shortest path spanning tree, depending on what the edge labels are, right? And we say if the edge labels are non-negative, Dijkstra always works. in the sense that it finds the true shortest path spanning tree. So here, we see that, so we can look at this, okay? When we start, so let's say, so again, I didn't say, we're starting at S and ending at D. I hope was that clear to everyone? Sorry, next time, it will be clear. So source and destination. So what's the, and then there's some edge labels here, and there's an X. Okay, and so the question says as X varies over all integers, from minus infinity to infinity, when will Dijkstra work and not work? That's what the question is asking. So independent of X, what's the first step that Dijkstra takes? Yeah? Okay, does everyone agree? What's the first step that Dijkstra takes? It's going to be S to A, right? Because it has two options. I can go S to A or S to B, and I'm going to be greedy, right? Okay, now, what's the next step that Dijkstra is going to take? Yeah. Again, independent of X, it's going to do this. Why? Because the cost to D is 2. Remember, I always compute cost from the source. So the cost is 2, and the cost to B, which is the other option, is 4. And then, after that, I'm done with this, but B is not there. So the next edge that we added will be this. So this is the, I wanted this in ASCII here, but maybe an easier way to draw this is like this. It's like a diamond network here. Okay, and so this is the first edge. This is the second edge, and this is the third edge. And this is the output of Dijkstra. Okay, notice it didn't depend on X. But obviously the true shortest path spanning tree would depend on X. Right? So we can now figure it out, right? So we just need to look, now it's not going to be the route to B. It's going to be, is there a better route to D from S, right? Is there a better route? So we know that Dijkstra's cost is 2. So as long as now the two things to compare, there are two routes to D from A. Right? One is cost 2, and the other is what cost? What's the cost of the other route? Yeah, 4 plus X. So you just need to compare this. You just need to set 4 plus X to be, so Dijkstra will work when 4 plus X is greater than 2. Yeah, right? And then, yeah. So what did you get? I think you were trying to tell me the answer before? Minus 6? Hang on. Let us, I probably should have been a bit more accurate. Let's call this a directed graph. Okay, so maybe this is a good example here of sometimes we'll have undirected graphs and sometimes we'll have a directed graph. So to remove any negative cycle stuff, we'll make it a directed graph. Okay, so now you cannot have a negative cycle. Okay, you have to follow the arrows. Okay, so what should the answer be? So what do we want? So Dijkstra will work when what? When it will work when 2 is less than or equal to 4 plus X, right? So what does that mean? That means X is greater than or equal to minus 2. Right? Did I get that right? Yeah. Okay, so you had something twisted around. No, I just want to make sure. I made this problem up, so am I right? Do you agree with me, or is... Yeah, so it will work when X is greater than minus 2, and it will not work when what? When X is less than minus 2. Now you could argue what happens at minus 2. At minus 2, both routes are the same. So, I mean, yeah, You want to say it doesn't work? Okay. You want to say it works? It's okay. I would say it works because it gives you, both paths are the shortest path and it gives you one of them. So we'll just say it works, okay? So it works with the equal to. Okay? So it will not work less than -2. Okay, so yeah, I mean, it's just want to just reinforce the discussion that we had last time about Daksha. Okay, good. Okay, let me give you my last example, which I thought might be interesting, about Steiner tree and spanning tree. So let's say, so I came with an example of a road network. So just let me, because in a computer network, I mean, it's just easier to show here. But you get the idea, okay? So let's say I have this road network and I put it on a graph so we can have distances, okay? So I have these 5 cities and I want to connect them. So what would like minimum spanning tree do? Minimum spanning tree, let's do that we'll do this in 2 different colors, okay? We'll do minimum spanning tree maybe in green. Okay, so we'd connect that. Then what would we do? Let's say I'm allowed to build roads however I want. But I want to have the smallest, and I put smallest in quotes. Sorry? Yep, I might do that. Then? Okay, then? Yeah. So how would we do that? I mean, you have many choices. Yeah, you could do that. That's fine. Or if you want, you could go from E to C, right? It doesn't matter. So this thing, so what's the cost of this? Or, I mean, that's why I put it on a graph. So what do we have? We have 10 plus what? That diagonal is 10 square root of 2, right? It's like a square, 10, 10. This is the diagonal. So 10 plus 3. 3 times 10. Actually, I should just write 3 times 10 square root of 2. So what is that? That's like, square root of 2 is 1.414. It's like 10.14 times 3 is like 30. No, what is it? No. 1.4, right? So that's 0.4 times 3 is 1.2. So this is 42, right? About a little bit over 42, right? So it's 42, so it's approximately 52, right? Okay, now let's see. So this is so the minimum spanning tree is in green. Okay, that's the idea. The nodes you're given, that's all you're allowed to use. In the Steiner tree, we're going to be a little bit cleverer. Let's make it purple. Okay. So Steiner tree will be in purple. So we'll still have this, but anyone can think of any ideas? If you're allowed to build roads. So you could ask, what's the smallest amount of road I have to build? Well, check this out. What if I build an intersection here? So what's the cost of this? Well, what do we have? We have 10. What is this? 10, 10, 10, 10. So what is that? 50, right? So you see, we can do better. We can use less road, less material, but that intersection is not part of my network. That's the difference with Steiner tree. You see the difference now? I mean, I like this example because it's very clear. Right? Like in a network, you can say, okay, can I add routers? Maybe. Or if you have nodes that are not in your multicast, you might still route through them if you can do better. And that's why it's a combinatorial hard problem, because you have a lot more things to check. Okay, is everybody clear on this? This is the difference between a minimum spanning tree and a Steiner tree. Okay, good. Okay, okay, so I'll see you all next week, and next week we'll do lots of problems because we need to talk about problems for TCP and network layer and so on. You also have some homework due. If you have any questions about the homework, please ask. Okay, and then I think the following week we have a test. Right, so this is week 11. Week 12 is next week. We'll do some review. And again, hopefully some more in-class activities, okay? I think it's good for you to get practice in doing stuff in class. Because, well, yeah, you know, and then ask questions if you have questions. Okay, and then we'll have tests next week. I'm also going to try to arrange, there's some things that we want to talk about real-world networking. There's some slides on that, so we'll cover that as well. And then I'll try to see if I can get some of my, I'm trying to arrange a guest lecture, see if I can get some interesting speaker. Okay, but it'll be during the class session. Okay, so thanks. If you have questions, I can stick around. Yeah.
For the test form, what's the test format?
The test it's going to be in class, and I mean pen and paper. It'll be some MCQ, some non-MCQ. Yeah, yeah. Okay, and you'll be allowed one help sheet. The help sheet can be A4, double-sided, handwritten help sheet. Handwritten, yes. You cannot use a computer, and you have to do it yourself. You cannot take someone else's handwritten. Okay? That's my little trick, okay? If you make your own help sheet, you will not need your help sheet. You see? So I'm up front. You know somebody did, actually, I'll tell you my little story in a second. Okay, hang on. Okay, so I think we're done, right? Okay, let's end this session.